So continuing on here with differential grouping of antibiotics, the example here is given for cephalosporins. You may have heard of this terminology that somebody says, oh, this is the first, second, third, or fourth generation antibiotic. You can take a look at the example here for the cephalosporins, but it's kind of good to have heard of the term first, second, third, or fourth generation antibiotic. Now we are moving on into antifungal, antiviral, antiprotozoan, and antihelminthic drugs. Let's start with the antifungal drugs. So those would be against fungi. Now the problem here is that fungal cells are eukaryotic cells, and that means that they're closer in the way they work to our cells. It will be harder to find selective toxicity drugs that are affecting the fungus but not your cells. So you can take a look at where are those cells now different, and there will be an obvious difference will be the cell walls. So you can expect antifungal drugs to act mostly on cell walls and try to exploit the differences between fungal cells and mammalian cells. So here the agents that are listed here that you should know: polyenes, the amphotericin B is an important one, so that we should know. Azoles, almost everybody has probably taken azoles, so there would be clotrimazole, other azoles that are on the market that are sold even over the counter as for athlete's foot, stuff like that. So this important group you should definitely know about, but you can take these guys off. Next, the echinocandins. Those are not so important for you guys, so we can take those off. And then agents inhibiting nucleic acids, the flucytosine, that would be a false nucleotide. It would inhibit RNA synthesis. Also not that important for you guys. Other antifungal drugs, and those are important: griseovolvin and tolnaftate, very popular drugs that are sold over the counter even. Tolnaftate, very popular drug to treat athlete's foot fungus, of course. And then moving on to antiviral drugs. Well, there you have to take a look at how the virus works. And so you can try to inhibit the entry and diffusion of the virus with your own plasma membranes, so inhibiting the entry. And then you can also inhibit the uncoating of the virus once it has entered. So here are some drugs that are on the market. You don't really need to know the brand names, but entry and fusion inhibitors as a class you should know about. Uncoating inhibitors you should also know as a class. And then we have drugs that prevent the genome integration or inhibit nucleic acid synthesis. They're the AZT. That one is used to treat HIV. That one you might want to know about, this one in particular. And then acyclovir. This one here is a false nucleotide. It inhibits DNA RNA synthesis. That one is given for people with herpes type of infections. A lot of times it's in creams that people take for when they have cold sores, as an example. Those would be the important drugs in this class right here, but there are quite a few in here that are trying to inhibit nucleic acid synthesis. Then assembly and exit inhibitors. Those would be protease inhibitors mostly, because these viruses, they need a protein coat, and if you inhibit the enzymes that will cut the coat to the right shape of the virus, then of course you would inhibit the assembly of functioning viral particles, and that's a good thing. Many of these are used in the treatment of HIV and hepatitis viruses. Interferons, those are substances that are secreted naturally by cells to warn neighboring cells of coming viral infection. And they used to have a really high promise. People used to think, oh, if we just had alpha interferons or interferons in general available as a drug, then it would be just as good a medication for viral infections as we have with the antibiotics for bacterial infection. It turned out to be not so true. Interferons have a relatively limited use as a drug. It's probably a delivery problem, but the interferons are available by, they can be made with biotechnology, but they just don't have the use that people had hoped for. Now moving on to antiprotozoal drugs. The chloroquine is a very old drug that's used to treat malaria infections. Lately, I'm not sure how this came about, that the hydroxychloroquine, people think right now that you can use it as a drug to treat a virus infection, which doesn't make sense to me at all, but hey, if it works, I'll take it. It's just the chloroquine or hydroxychloroquine, these are classic antiprotozoa drugs that are used for infections with, protozoa. And how they could possibly work as an antiviral drug, I'm not sure, but maybe the clinical trials will show us how that might work. So you should definitely know the chloroquine as an antiprotozoa drug. The other ones you don't need to know by name. Antihelminthic drugs, those are drugs that are used against worm infections. Probably the praziquantel is maybe the one that you've heard about. Maybe that your dog got treated with that. So there you should, parental, these two maybe you should know. So these are pretty famous drugs that are used to treat worm infections. A lot of times for your pets they will be used if your dog has a tapeworm or a roundworm infection. Okay. Now we'll take a look more specifically how these antibiotics or groups of antibiotics work. Inhibitors of cell wall synthesis, of course the first one, the original one, penicillin. How does it work? Well, they contain a beta-lactam ring, and the beta-lactam ring prevents the cross-linking of peptidoglycans and therefore interferes with cell wall synthesis, with the construction of functioning cell walls. They work best with gram-positives because, as you know, the gram-positives, they have thick peptidoglycan layers, and therefore the penicillins naturally would work best. So let's take a look at this here. The natural penicillins, there's the penicillin G and penicillin V. They have a relatively narrow spectrum of activity, but those natural penicillins, they're very susceptible to penicillinase, which is the bacterial solution to the problem of being killed by penicillins. And then the semi-synthetic penicillins, these are penicillins that were altered in the chemistry lab. So semi-synthetic means that you're taking a natural substance like penicillin and then you're altering it in the chemistry lab. So they have added side chains, basically making the penicillin more resistant to penicillinases. And so therefore now the bacteria have to come up with a new strategy, a new trick to get rid of the penicillin. So here we have natural penicillins. Take a look at the beta-lactam ring. That's this box right here. Here, very similar. So this is the part of the molecule that specifically inhibits the cell wall synthesis of the peptidoglycan. In the semi-synthetic penicillins, you still see the common nucleus. You just see that there were some modifications to the overall molecule were done, and that increases its use a lot of times. It also makes it more resistant to penicillinase, for example. But all of these penicillins, of course, are still working best against gram-positive bacteria. And here are the ampicillin with an extended spectrum, slight modifications right around here. So, but the common nucleus is staying the same. And here, just briefly, we have sort of the retention of penicillins, the concentration of blood after injection or after you taking it orally. You can take a look at it. It's very inconvenient if you have a drug that has a very short half-life, meaning it's being degraded or excreted from your body very quickly. that is very annoying because that means you need to take a new dose very quickly again. Here, the effect of penicillinase on penicillins. So basically there's an enzyme, and if bacteria have this enzyme available, they can just cut open this beta-lactam ring, and now it's no longer harming them, and cell wall synthesis can proceed as usual. So any bacteria that have this enzyme, penicillinase, they can just cut up what's making them sick, the penicillin here, the beta-lactam ring, and then they are no longer harmed by penicillins and their derivatives. Okay. So here are some sort of the answer, the next generation antibiotic that then came out. Those would be penicillinase resistant penicillins. And in this case, we have methicillin and oxacillin. And you've probably heard of methicillin resistant Staphylococcus aureus. That would be the MRSA. And if they are resistant to methicillin, that means now you lost. If a bacterium is now resistant to your penicillin resistant penicillins, then, well, you've lost. They have basically won the battle. And it's very dangerous if you have methicillin resistant bacteria in hospital settings, for example, because you really don't have anything on the shelf to treat those infections. Extended spectrum penicillins, they are then working against a broader spectrum of bacteria. There we have the Ampicillin, Amoxicillin. Those are very popular antibiotics, have been widely overused. They come in bubblegum flavor, and it's basically as soon as your kid has an ear infection, they will give you a prescription for this. It's probably changed by now because the resistance is such a big problem. Then we have penicillins that have a beta-lactamase inhibitor added to them. That's another trick they're trying to use to kind of still inhibit the bacterial growth, but it does work to some extent. So it's always sort of an arms race. We come up with something and the bacteria find a solution to get around it. Here more inhibitors of cell wall synthesis, the carbapenems. They substitute a carbon for sulfur and then add a double bond. So it's just some modifications, chemical modifications. Monobactam, also just some chemical modifications that you are doing to the molecule to prevent the bacteria from getting around it. Here, the cephalosporins, they work similar to the penicillins, but the beta-lactam ring is different from the one that you would find in penicillin. And we already talked about that they are grouped according to generation of development, like first, second, third, fourth generation. Then we have the polypeptide antibiotics, the bacitracin. That one is really only used in topical applications. So in your triple antibiotic ointment there, you would find the bacitracin. It works great against gram-positive bacteria, but only used on the skin. The vancomycin is a glycopeptide antibiotic. That's sort of the last thing you have against methicillin-resistant Staph aureus, the MRSA, this one right here. Now, they are the vancomycin-resistant strains as well, and then you really are out of luck. You have nothing on the shelf anymore. So vancomycin-resistant bacteria, this gets really scary because they have basically outwitted us, and these bacteria have come up with a solution against all of these substances that are supposed to be toxic to them. So here are the nucleus structures of cephalosporins and penicillins compared. You can take a look at that. I'm not going to make you know these specific chemical structures, but you should be able to identify the beta-lactam ring, this square right here, similar right here, the penicillin nucleus. And then here we have antimicrobial antibiotics. The isoniazid inhibits the mycolic acid synthesis in the mycobacteria, and the ethambutol inhibits incorporation of mycolic acid into the cell wall. Both of them can be used, of course, for the treatment of tuberculosis.